So we want to focus on software techniques to improve the efficiency of AI. And in particular, we'll chat about how to apply that to medical domain in this talk. This is some of my prior work using deep compression techniques to drastically reduce the model size, make it 10 times smaller, but preserves the accuracy by pruning and quantization. Pruning reduces the redundant connections, quantization reduces the precision for each connection. And we worked on a hardware accelerator that can directly work on the sparse and compressed model called the Efficient Inference Engine, which is the top 5 most cited paper in the 50 years of ISCA. And you can see the top 2 is the in-data center performance analysis of TPU, is Google's TPU paper. And this year's model compression is widely used, and the number of publications on pruning and sparse neural networks is growing very fast. So my current work focuses on the following aspects, from software to hardware co-design, from tiny model on mobile device to large model on the cloud, using sparsity to accelerate models, using quantization, low precision to accelerate the models, accelerate both inference and training, from discriminative model to generative model. Later we'll show some generative AI examples that is deployable on a laptop, from single modality to multiple modalities, in particular, visual language model. In the elevator, we chatted about analyzing the image for the eyes, etc. Hopefully that can be helped. So let's start with LLM quantization, how to accelerate large language models. So quantization is a good technique, but we find large language model contain a lot of outliers, making quantization very difficult. So we propose a mathematical equal transformation so that we can push the quantization difficulty between the activation and the weights. So that previously we need 8 GPUs to serve this model, now we need only 4 GPUs. So that saves a lot of compute cost. So previously, this is the memory consumption, and we can reduce the memory consumption by half. And the speed, although you reduce the cost by half, the speed maintains the same. So if you have a product, you want to expand the deployment and save the cost, this is a very good way by using smooth quant to quantize models to 4 bits. And we are not satisfied with 8-bit quantization. We further pushed the quantization precision to 4-bit so that we can deploy large language model locally on a laptop. So this is adopted by NVIDIA's chat with RTX. If you have a laptop, you can chat. You can deploy your 7 billion or 13 billion parameter large language model. For doctors, I believe this is helpful since you can carry your laptop to see the patients. You no longer have to rely on a server. And everything is stored locally. This is writing the code, sorting an array in C++. But with the same capability, we can run 7B or 13 billion parameter model on a laptop. You can carry a laptop, see your patients. And this, the basic idea, I will go through very quickly. We find not all the activations are equally important. So when we are quantizing the weight to only 4-bit, we want to look at the activation. If the activation is big, we want to preserve those weights. How do we preserve it? We scale it. If you scale it by 2, previously 0.5 and 1, they are both going to be quantized to 1, right? 0.5 and 1, they both get quantized to 1. But if you multiply by 2, one is 1, the other is 2. Now you can distinguish them. Using the simple heuristic, AWQ, the activation-aware weight-only quantization, can quantize large language model from 16 bits to 4 bits, so that it's smaller and run faster. We further designed this tiny chat computer. So this is a very small 3D printed computer. Inside, it's running a Llama 2 7B model, giving some attractions in Boston, like the Museum of Science, Harvard Square, etc. In the back, you can see it's powered by a very small computer. It's a embedded Jetson Ori Nano in the back with only 8 GB of memory. Since we compressed the model by AWQ to only 4-bit, we can fit the large language model inside this mobile device. So TinyChat is open source library that can support this 4-bit quantized large language model. Even if you don't have access to the internet, when you have low power devices, resource constrained devices, privacy preserving scenario, like you don't want to send some patient's information to a cloud, this is a perfect scenario to deploy a large language model. So smooth_quant and AWQ is very widely used by industry. Hugging Face, which is the GitHub for large model these days, AWQ has more than 15 million downloads over there. So lots of companies are using TinyChat and AWQ to deploy a large language model on the GPUs, on the CPUs, on the laptops, on mobile devices, etc., including NVIDIA, Tensor RTLM, Intel Neural Compressor, Q8 Chat, 8-bit Chat, IBM, Berkeley, and Hugging Face, and several startups. So it's using a commercial-friendly license, so it's free. Feel free to deploy it. Okay, now let's switch gear to talk about multi-model large language model. Okay, so what is multi-model? We want to handle not only text, not only language, but also vision tasks. We want to understand images. We want to understand videos. So this is an example. Given this image, we can ask, what is unusual about this scene? Are there any safety concerns? Okay, and the assistant can tell you that in the image, a person is hanging from a rope attached to the wind turbine blade. This is unusual and potentially dangerous situation as it involves climbing a moving object high in the air. There are several safety concerns associated with this activity, such as the risk of falling from a significant height, getting injured by the blade or other parts of the wind turbine, right? So it can have very detailed explanation about what's happening in the image. And we can actually deploy this model locally on a very small device. It's a JSON ORIN. It's a JSON ORIN size of a palm, AGX ORIN, and then it can give you the answer in real time. We can ask some other questions. For example, how many cars are jacked up? There are 2 cars jacked up. There's a person whose head is under the jacked up car. What color are his gloves? And it says orange. What its brand is the car? It's a Jeep. What is unusual about the traffic situation in this image? It says a large number of cars on the road. There might be some event. So we want to try different views, not only visual, but also aerospace. So what is unusual about this image? Some deer crossing the road. Not common for deer to cross the roads. Should the driver honk at the animals, and why? It's generally not recommended to honk at animals, potentially leading to dangerous situations. They can slow down and stop their vehicle. Okay, so the good thing about this is that for self-driving scenario, it's not always possible to collect all the corner cases, like deers crossing the road. Very few images or scenarios corresponding to this. A visual language model can help the model to integrate what we learn in the common sense from text. Since in the textbook, I believe we learn most of the driving skill not only from driving school, but also from common sense. Right? Common sense comes from our readings. Like when we read deers, when animals are crossing the road, we should not drive. Right? Even if we don't have such training image, the model can generalize those word knowledge to these corner cases. And let's see, how is this done? Okay, so we have a large language model, we have images, we have text. So we pass through the image, feed it with a vision transformer, which is frozen, and we have a projector to project from the image space to the language space. Okay, so we have visual token concatenated with the text token, and on and so on, but interleave the image and text, and we treat image as text. Okay, we have visual token, we have text token, and we feed it to the large language model. And here, make sure we have to fine tune the large language model, since it not only take languages, but also it takes images. Okay, so the tokenization process is very important. So after tokenization, everything becomes tokens. Image are tokens, text are tokens, videos are tokens. The voice is also tokens. So everything is tokenized, token in, and then token out. So this is the fundamental idea. A very interesting feature of VLA, visual language model, is the in-context learning capability. So let me see. Given the first image, we have two images right here. The question is, how much should I pay for all the beer on the table according to the price on the menu? So initially, the answer is wrong because it didn't use the prompt step-by-step chain of thought. But if we add the visual chain of thought, adding think step by step, very simple prompt, the answer is right. The beer on the table is a magna, so it has to first do object detection counting, which priced at 6. You have to see the menu on the bottom and see actually the price for magna is $6 per bottle. And there are 2 bottles of magna on the table. It has to count number of magnas. Therefore, the total cost of the beer should be 6 times 2, should be $12. So we can reason across multiple images. In particular, I think for eyes, for medical, this might be interesting since you have 2 eyes, you have to associate left eye with right eye, and also patients usually have to track the progress across multiple years. Like here, from 1984 to 2012, what's the implication of temperature based on this image? And here it says the image shows a comparison of Arctic ice cover in 1984 and 2012 has significantly decreased over the years, which is a result of climate change. The reduction of ice cover can have various implications, such as increased exposure of the Arctic environment to the warmer temperatures, etc. Right? So comparing across timestamp, like if a glaucoma patient want to compare his eye from 10 years ago to current stage to see if for example, cup over disc ratio has changed, whether the nerve fiber thickness has changed, whether there's some subtle difference. Previously, doctors have to rely on a lot of experience of years of training, and that can have a lot of workload. But if you feed the eye image from 10 years ago to current image and feed it to visual language model like VLA, then it can tell you the difference and see if the glaucoma is progressing or not. In the healthcare, VLA can also help monitor patients' status. It's purely using zero-shot learning. So zero-shot means we never fine-tuned it. We just use the same model we previously trained and give it a new task for patient monitoring. What is the patient status? The patient is in a critical condition as indicated by the presence of ventilator and fact is hooked up to a lot of wires. Is the patient asleep? Yes, the patient is asleep. And another zero-shot learning scenario, the same model can be also applied to driving. So that's the power of large language models. It has a lot of word knowledge and generalized super well. But what is special about this driving scenario, what should the driver do? Foggy condition can be dangerous, such as reducing the speed, using the low beam headlights and keeping a safe distance from other vehicles. And previously, in the car or outside the car required 2 models. Now, 1 model can do both. So this is driver monitor system inside the car. It asks, is the driver distracted? Is the driver on the phone? How many people in the car? Where is the passenger sitting? And here is a smart factory. How many chip bags are picked up by the robot arm? So this is a video. Can understand not only still images, but also videos, which is multiple frames of the images. And it can also do some math and reasoning. The 8 input images are sampled at 2 frames per second. How long does it take for the robot arm to pick up 1 chip bag? And the robot arm takes 1.5 seconds to pick up the chip bag. And again, thanks to TinyChat, this Villa visual language model can run on just a M1 MacBook CPU of a M1 MacBook. For example, here we can ask what is the name of the painting. It says it's portrait of Mona Lisa. And who drew this? It says Leonardo da Vinci. So you can just use your laptop to run this 7 billion parameter visual language model. Okay, and at NVIDIA, we built this MONAI multi-model visual language model M3, Villa M3. Okay, so which is might be more related to hospitals. Okay, so Villa M3 is a follow-up work fine-tuned on top of Villa. It's a visual language model for medical applications, for focusing on addressing the unique challenges for vision language models when applied to medical domain. For example, we can have expert input in medical models, can integrate expert knowledge into the model, focusing on precision domain knowledge, versus Villa itself is a general purpose model. This is a highly specialized model for medical. It used the Villa base model. Okay, so every time when our team is improving the Villa base model, we ship it to the Villa M3 team. They build on top of the Villa base model to fine tune it on the healthcare specific data sets. And I think there is a lot of room for us to collaborate. And it also has the feature of hybrid information fusion. It can incorporate 2D, 3D, even 4D information formation by fusing the expert model results and VRM predictions. An amazing thing is that MONAI module is open source. So this is the project page. There are several fine-tuned checkpoints released as part of the project MONAI. So feel free to try it out. So this is the project page. Oh, there's no Wi-Fi. Let me connect to my hotspot to see if I can show you this thing. This is the GitHub. It's an open source Mona M3. So this is the architecture. Okay, so you have a input. It could be a single image or multiple image, feed it with the user prompt. We train this Villa model, which contain two parts. One is the large language model. The other is a VIT, vision transformer. It has several expert models specifically for different domain. And then it can give expert output like segmentation, classification. And the large language model can also give the, visual outputs such as VQA, visual question answering, report and finding generation. So all the code and training data and is released. So feel free to check it out. And the Villa code base is also released and open sourced. So this under NV Labs, Villa. Right here is the title is on pre-training for visual language models. We also make it deployable using TinyChat and AWQ. And next week, actually this Thursday, we are going to release a new version of Villa. So stay tuned. We also release this long Villa, which can handle long context. So you can understand very long videos and very long inputs. So if you increase the number of frames for the video, previously it will get out of memory since there are so many images. Like medical records, you may have a lot of medical records. You will soon run out of memory. But using long Villa, you can still make it within the memory and also make it faster. This is y-axis is the GPU hours to train. So this is on Villa. It's part of the Villa project. So these are some benchmarks, and here is some video demo, like understanding exactly what is happening in the video to elaborate the visual and narrative elements of the video in detail, so you can tell the person's hand working on a white surface, etc. So here we open sourced the training pipeline. So if you have a data you want to train from scratch, you will just follow this Step one is to do the visual and language alignment, make sure the vision and language, image and text, they're projected into the same space. And then large scale pre-training using MMC4 and COYO datasets, very detailed instructions, and then supervised fine tuning. And then we provided the evaluation benchmark and also the video benchmark and also the inference techniques. For example, you want to deploy VIA on your own server or on your own laptop, just follow the instruction here step by step using, and also we provide techniques to quantize the model to 4-bit so that you can deploy on a laptop. Also, VIA API server is also available right here. So if you want to try the demo, you can just navigate to vila.mit.edu. And here we provided several examples. You can also upload your image that you like. For example, this is the multi-image input we can try. It's using my mobile phone's hotspot, so it's a bit slow to upload the images. So I input these two images and we ask what is the implication of temperature based on this image. Yeah, and it's going to tell the implication temperature is that the temperature is increased over time. This is evident from the melting of the ice caps on the Arctic region. So you can use this free interface to input your images and see what is going to output. So this is the academic prototype, vila.mit.edu, and at NVIDIA, we have built it into a NIM with more professional serving. So this is the Vila service provided by NVIDIA using Vila. So it's a multimodal vision language model that understands text, image, video, and creates informative responses. So this is the video, default video. You can see there is a worker coming into the frame, trying to secure a tape to block this aisle. And then we can ask Vila what's happening in the image, in the video. There's also a button you can upload your own image or videos. We ask, elaborate what the worker is doing, why he would be taking this action, and also provide information on what he's wearing. It's generating. It also has this JSON output so that you can plug it in to output some function calls, right? To automate the whole process. So the current preview is for human to understand, and the JSON output is for machines to understand. So you may possible to automate the entire process by building an AI agent that can read your screen and take action according to what's happening in the screen. Let me refresh here. Don't know if it is due to my laptop's issue. Oh, here. The worker who is wearing a neon vest, black pants, and a yellow hard hat is putting a yellow caution tape across the aisle. The action suggests he's cordoning off the area, likely for safety or maintenance. The caution tape is a common safety measures, no safe to enter or would require special attention. So it can give very detailed understanding about what's happening in the video. And also here you can input your own video or multiple images. Feel free to give it a try. All right, so we go back to our presentation about MONAI VLM. This is the architecture combining expert models and also multimodal LLM, which is VLA. And here are some examples using MONAI. It is also, the demo is also available right here. I can share the slides later. So you can upload a medical image. And here we can ask it to, can you identify any liver masses or tumors, okay, and can ask a lot of questions. So let's see the demo. So let's select some chest X-ray sample, and then we can ask some questions. Looks like this is a chest X-ray, and let me trigger first trigger this expert model and says no, there's no such disease. And then we can do some other tasks, a CT sample, and then segment the entire image. We submit. And then it's going to segment the whole image. Just using like conversation, you can input whatever you want. Isolate the cardiovascular system in this image. I located the cardiovascular system using this expert. Okay, so this is the MONAI multimodal model visual language model demo. This is the segment, everything. And this is another question is this pneumothorax? The user says it looks like there's a chest X-ray. I mean, let me trigger this expert and says no. And on the bottom is having a lot of classifications right here to combine the expert models and before giving the final answer. So this is showing the power of combining this multimodal visual language model with medical tasks. I believe there will be a lot of opportunity in multiple domains. Okay, so let's switch gear from understanding image and language to generate image and language. Okay, so let's talk about high resolution image generation. So generating image is pretty hard because you need to do pixel-wise prediction. It's very computationally consuming. We can lower this cost by building a very efficient image generator, hybrid autoregressive transformer, which is up to 7 times faster with similar visual quality compared to using diffusion models. So conventional methods are using diffusion model to generate image and video. We took a new approach, not using diffusion model, but using the autoregressive transformer, similar way to language models, where you generate language tokens, now we generate image tokens and put them together. Now it's photorealistic images. All these images are actually generated by heart. You can see how much detail we have, like the eyes, like the color, like the details, the hair, etc., the lips, and the model is much faster compared with prior art. We can also try some demo. Let's go to heart.mit.edu. For example, here we can generate something like a melting apple, and then you can just take 1 or 2 seconds to generate each image super fast. Or Thanksgiving turkey. Thanksgiving turkey, right? Or Halloween pumpkin. And this is running on old A6000 GPU, not even the H100 or A100, very old GPU. It's even runnable on a laptop due to the model is so lightweighted, so fast. It's auto-regressive. You can take advantage of all the optimization techniques like we did for TinyChat, for AWQ, so that you can deploy it locally on your laptop. Okay, so this is hard auto-regressive transformer. And compared with the right-hand side, those are the models we're using diffusion technique, like Playground, PixArt, XDXL. The left one is ours. You can hardly tell the difference, the quality difference, which one is better than which. And this is a demo showing how it can be deployed on a laptop. Here, we give some input prompt on this laptop, and within 2 seconds, it can generate the image. And try some other examples. And this model is also open sourced, so maybe you can generate medical images to train other models to save the time for collecting the data. By the way, this model is trained on purely on synthetic data. This might be particularly helpful for generating corner cases where the normal image might be easy. Lots of people, the normal case, but abnormal case might be rare. And we can use such generative model to generate rare cases to train the visual language model to understand some rare diseases. And we have another work called deep compression autoencoder. Since generating token is very expensive, tokens are very valuable, right? So we want to reduce the number of tokens. That means we can reduce the workload. Prior work can reduce the token by 32 times on each side of the image, by 8 times actually. If you go up, the compression ratio, as the compression ratio go up from 8 to 32 to 128, the quality degradation is very fast. FID, actually, the lower the better. So conventional work cannot have compression ratio larger than like 32. But for ours, we can also push the frontier to 128 on each side. So that's 32 times larger on each side, 1,000 times larger compression ratio on the whole image without degrading the quality. The quality is very well maintained. And you can compare our tokenizer autoencoder compared with stable diffusion, stable diffusion, the variational autoencoder. Under 64 by 64 compression ratio, stable diffusion's autoencoder is very poor quality, but ours very well maintained quality. And using this deep compression autoencoder, we can build a much faster diffusion model. Like here is the baseline diffusion model. This is the stable diffusion. You see the speed is very slow. It can generate 17 images per second. And this is ours, so we can compress the latent space to a much smaller patch, 8 by 8, previously 64 by 64, and we can generate a much larger number of images per second. And with that, we built the SANA, high resolution image generation. Okay, so previously, prior art can build up to 1K by 1K. We can build 4K by 4K. And 4K, you can see a lot of details compared with 1K. And this is the 4K resolution image we generated. You can see the ship, so many details. Look at the ocean, look at the air, the lighting, lots of details. And this can fit in a single GPU again. So it's about 100 times faster compared with the prior model like Flux. And the speed 100 times faster comes from the model architecture, and then deep compression autoencoder 10 times faster, and linear DIT rather than quadratic growing complexity, kernel fusion, the GPU kernel design, and flow-based DPM solver. And combining all these techniques is 100 times faster. These are the images generated by SANA. It's even better quality than HART, using only 1.6 billion parameters. The text, the human, the letters, some imaginary stuff, some neon lights, different stuff. And this is a glue porch, 356, parked in front of a yellow brick wall. And an old rusted robot wearing pants and a jacket riding skis in the supermarket, and everything can be generated using a single GPU. So let's also see some demos. So just navigate to nvsana.mit.edu, and we can open this free service for Sana. It's deployed in the basement of my lab using only 8 3090 GPUs. And we have so many users so that we expanded the number of GPUs from 1 to 8. And you can see there's a lot of users. We launched it within a month, already have 400K users. So let's try some demos. This is a portrait, a photo of a girl, photograph, had a detailed face, depth of field. We can also try professional portrait photo of an anthropomorphic cat wearing a gentleman hat and jacket walking in autumn forest. We can also adjust the width and the height. And then we can also change some style, maybe neon punk style, and then we can generate again. Right, this is in a different style. Can also understand multiple languages, like even poems. Let's try some other prompts. Using the neon lights style, and then we can try some cinematic style. Make it larger. Right. And I can even understand emojis. So for example, this one, a dog wearing sunglasses flying on the, okay, right here, right? And it's pretty fast. This is currently using GPU 3, just a single GPU. We did some load balance across these 8 GPUs. Can further zoom in to see the amount of details for this 4K image. Okay, so feel free to try it out on yourself at nv-sana.mit.edu. And again, this is also open source, also deploy on a laptop. All right, with that, let me conclude my talk, leaving some time for QA. So we have all these techniques. If you are interested in learn more about that, we have efficientml.ai, which is the lecture I opened this year to talk about efficient deep learning techniques, covering efficient inference, using pruning, quantization, neural architecture search, efficient training, how to make training faster by using distributed training, on-device training, gradient compression, so that you can use fewer GPUs, less memory, the model faster, and also application-specific optimizations, in particular large language model, diffusion models, autoregressive models, video and point cloud, covering system and algorithm co-design. So everything is openly available. You can just navigate to efficientml.ai. Let me zoom in a little bit. So we have all the lecture slides and videos and even labs. For example, if you're interested in like vision transformers or diffusion models, you just click the link. Actually, the slides and videos are all available right here. So feel free to check out those details at efficientml.ai. Last year, there was about 2 years ago, we opened the course. There are about 30 students. Last year was 90. This year is 220 students. So it's very well welcomed class. Yeah, so these are some of my students. They went to UCLA, it's faculty, UCSD, NVIDIA, and OpenAI. Some of the awards my student received. All right, that's all my presentation. Thank you.
Two questions. I see this. So since the application is so efficient, work like implement any of this model in mobile. It's, these days everyone has mobile phone. This is one question. Second is even in medical, we have 3D medical data. And myself is working on like a blind navigation, so we need to understand the 3D layout, 3D. So these are all 3D. Can you or have you done anything like using the AI model to understand the 3D, the layout?
Yes, actually, for the sake of time, we didn't have time to cover, but we did do a lot of work on 3D understanding. For example, torch spars, and this is the BV fusion. We want to combine both 2D branch on the top and 3D branch on the bottom, 3D point cloud and 2D camera, combine fuse information together so that in the driving scenario, we can understand the 3D world. Combining the camera and also the LiDAR sensor, we can understand the segment, the road, the drivable area to do 3D bounding box detection, spatial understanding. And this also require efficient system support. So we designed the torch sparse library to accelerate the 3D object detection, 3D object tracking. This is some of the award we received for 3D understanding.
So, is this a visual language model?
No, this is the BV fusion. This is before the large language model era. This work was done in 2021.
So any visual language model is pretty specialized or good at understanding 3D.
Yeah, the VLA 3D is coming out very soon. So we will have this feature in the large language model in VLA as well. Maybe in 1 month, if you check out our website, in 1 or 2 months, we'll have the VLA 3D available as well. And the other question is development on the mobile. So we have a lot of mobile deployments. Actually, for example, this is on-device training. This is on
video. You show them?
This is actually on microcontroller. It's even smaller than a phone. It has 2 buttons. You can click the button to train it with people, without people, etc. We also have an on-device pose estimation called Light Pose. GitHub. It's also open sourced. So basically, our work is doing on-device pose estimation. Somehow the demo didn't show up, maybe due to my phone. Due to my phones. Oh, there we go. Yeah, this is running locally on the phone, finding the key points of the human joints. Might be also helpful for identifying the key points in the eyes, in other X-rays, etc. And this is runnable locally on the phone. Yeah. Right. So after 4-bit quantization, 7 billion parameter model becomes only 3.5 gigabytes. So many phones have that memory.
I have one question. How your data model is trained? It's trained from scratch or based on some other open source model? And how long is the training like using how many?
Yeah. It requires about 128 or 256 A100 GPUs to train.
A100.
A100. H100 can cut it by half, 64 to 128 H100.
The training for how long?
Training for 3 days to a week. So it's still doable, still manageable. And since we already have a good base model, if you want to particularly tune it for eye image, I would imagine it'll be much faster just to supervise fine tuning with like 16 GPUs or even 8 GPUs, I think is doable to fine tune on subtasks.
We have started to use the Villa and try that to fine tune for surgical ocular video. And it is not finished, so we are in the middle of that. So till now, what we found is that it is depends on what are the prompts. For example, we just fine tune for 2 or 3 prompts, not so much. Okay. So for example, once we ask about okay, what's happening in this video, the answer is too much. So wide. For example, okay, it's a video of someone playing or something. But once we ask that, is it a cataract surgery? The answer is yes. It is cataract surgery. So what's your opinion about how we can resolve that issue?
Oh, yeah. So prompt engineering matters a lot, and I can introduce a few good techniques. One is visual chain of thought. The other is few shot learning. So let's see if I have some detailed example right here. Yeah, chain of thought basically says you first give some example, like 2 shot. You give 1 shot, 2 shots, and then another desired one. Like first image, the company is famous for search engine. Second one, company is famous for iPhone and Mac. Third image, and then it's going to say famous for GPUs. So you can give a desired output, give several examples, and they can, for example, all your examples are pretty short. Then the answer for new input will be pretty short. It will mimic, follow the previous example. This is called few shot learning. And the other prompt technique is called chain of thought. Chain of thought. Let's see if I have some example here. Let me verbally describe that. For example, you want to tell how many, how much should I pay for everything on the table, right? When you are training that, you should give the output, not just give one number, like $100. That's not a good training data. A good training data should be, there are 3 dishes on the table. They are A, B, and C. The dish price for A is $10. Dish price of dish 2 is $20. Dish 3 is $30. So the total price on the table should be 10 plus 20 plus 30, which is $60. Answer should be 60. That's called a visual chain of thought. When you are preparing the training data, you can fine tune your model on such visual chain of thought data, so that given a new task, like a reasoning task, it can do such reasoning first before it hallucinates. So that's a very effective technique. And the third technique, we can have a long discussion about, but third technique would be using inference time scaling, just like GPT-01, right? You can give multiple answers. You can give answer, let it think about it for a bit to understand if there is some drawback, and then let it answer it again. Or you can use Monte Carlo tree search, just like AlphaGo, to give a reward to balance between the exploitation versus exploration. Give multiple rounds. That of course increase your serving cost. But I believe these tiny chat efficiency techniques will help more in the inference time scaling. I think that's a very exciting thing to explore, since previously people talk about training time scaling. Now there's another dimension, inference time scaling.
Yeah, I have a question. And yeah, Vela is a very language model, and for image and video understanding, Vela is a very language model, and it's for image and video understanding. And Heart is a generative model, and but recently there's some model that combine the very language model and so Janus. So maybe in the near future, will you?
Yeah, we have that. Yeah, Vela U unified. Yeah, you can do both understanding and generation in a single model. That's a very hot topic.
But yes. My question is that it will be better if we combine them together. We can obtain the higher performance, or can make better understanding and generation.
Yeah, that's a good point. That's a very good point. Like this VLAU can unify understanding and generation. So far, we find, yeah, you can see it's describing what's happening, and then you can let it generate something as well. Generate a snowy mountain. So this is the same model doing both. We begin to see some publications showing generation can assist understanding, but I think it's still in the early stage of research, probably due to the available training data.
So it is a right way in for the AGI, or yeah, I'm not sure. I mean that it is the right way to AGI or in the next generation models. I'm not sure.
I think so. I think different modalities, you want to put them together and everything basically maybe put it in the homogeneous manner. Everything you can tokenize everything. So that require a lot of interleaved image, text, video, audio data all together. Require a lot of training power. So far, in VLAU, we don't believe we scaled it up to the desired scale we can afford. Like we don't have that many GPUs, but I believe this kind of unified foundation model would be super interesting. And we already show some promising results showing that if you can generate an image, you can do robotics tasks better. Previously, you just give an output, it should turn left, turn right. But now you want to give an intermediate state. This is called world model. And then to guide where it should move, that gives a better result. And that is exactly using VLAU to output not only the action, but also the intermediate image. It can let the robot think about, oh, what is the next state look like? And then it can do the action. It's better than directly do the action. Yeah.
I have another question. I also found that there is another model named Vita. So, but I couldn't find more information about the Vita. And is it VITA? And it's talked about that, okay, at the first it was that Vita is image based, cannot analyze video. So this is Vita on the NVIDIA website actually. So is Vita embedded right now in the recent version?
Oh, yes, it's already integrated together. So if you go to NVIDIA VLAN name, this is preview version, this already understand the videos like this one. So this is the unified place to go. Yeah, if you want to talk to these folks or try these APIs, or I can help, I'm happy to help you connect to the NVIDIA folks.
Prepare some clarification.
Oh, thank you.
Thank you for all your attendance.
On the next floor. Or behind, it's under your feet. That's your feet.
我可以把它 share， 如果发邮件我可以 share， 没问题。
That's great.
Probably